Now we will continue our discussion of the RL circuit, and this time the switch S2 is thrown to position B. Remember that in our previous discussion it was thrown to position A and RL circuit was connected to the battery, and this time it's basically disconnected from the battery, and resistor and the inductor are connected basically in series. So if we write Kirchhoff voltage law for the second loop here, if we define our current flow direction convention to be clockwise, since current flows in the direction of voltage drop, we have plus minus terminal on the resistor in this direction and on the inductor in this direction. So the voltage drop on the resistor is I times R, the resistance, and the voltage drop on the inductor is L di dt. So it is L di dt. And since there's nothing else in this circuit, these should add up to 0. So when I go back to the position where I started, so this is equal to 0. And this gives me the following equation: I times R divided by L is equal to minus di dt. All right. So if I take time to one side and the current to the other side, I will obtain an integral from time t equals 0 to time t minus R over L dt prime is equal to the integral. The value of the current at t is equal to 0 was epsilon divided by R. That's what we found in the previous case. So you can see it asymptotically reaches epsilon divided by R, and then we switch the position to B, point B. So we go from epsilon over R to the value of the current at time t, and I introduce dummy variable I prime, di prime divided by I prime. So I've taken I to the right hand side, time to the left hand side, and the minus sign is here. Okay, so this integral gives me minus R over L t prime evaluated between 0 and t, it's minus R over L t. This integral gives me natural logarithm of the current. So I find that natural logarithm of the current evaluated between epsilon over R and I is basically natural logarithm I at time t divided by the I at time t equals 0, epsilon over R. This is equal to minus R over L t. So that's the result of this integral. So I can see that if I take the exponential of both sides, the current as a function of time will be epsilon over R e to the minus t divided by tau. Tau, time constant, is equal to L divided by R. So this is basically our final answer for the current as a function of time. So we can see that the current basically drops from epsilon over R to 0 with a time constant L over R. Okay, so the inductor opposes the decrease in current and causes it to decrease exponentially. So basically that's what we find, the current decreases exponentially. If you look at the voltage on the inductor, L di dt, you will see that this is, if you take the time derivative of this, so let's do that. What is di dt? Di dt is equal to minus epsilon over r multiplied by tau multiplied by 1 over tau, which is r over L, e to the minus t over tau. So r's cancel, so we find that this is minus epsilon over L e to the minus t over tau, or in absolute value we see that the current, the rate of change of current is basically decreasing from epsilon over L to 0. Time rate of change of current is a maximum at t is equal to 0, which is the instant at which the switch S1 is thrown closed. So this is the value when S1 was thrown closed. Okay, so we have finished our discussion of the RL circuit. First, it was connected to the battery with electromotive force epsilon. We found that the current asymptotically approaches epsilon over R, and the voltage across the resistor increases to epsilon over R. The voltage across the inductor decreases to 0. Initially at t is equal to 0, it's epsilon, and the time constant of the circuit is epsilon L over R. And when we change the position of the switch to B, this time we see that the current decreases from epsilon over R to 0 exponentially, and the voltage on the inductor basically shows us that the inductor opposes the decrease in the current. The di dt starts from epsilon over L, so it's L di dt, which is epsilon. So initially we have epsilon for the voltage, and now it decreases to 0 as time goes to infinity.